What if everything we think we know about the universe is just the tip of the iceberg? What if, beyond the stars, galaxies, and the vast emptiness of space, there are hidden forces and fields that shape reality in ways we can barely imagine? These invisible threads, woven into the fabric of existence, might hold the answers to questions we haven't even thought to ask yet. Today, we're diving into the mysteries of the cosmos to explore 30 groundbreaking theories about the universe's hidden fields. These ideas don't just challenge our understanding of reality, they hint at secrets that could rewrite the rules of physics as we know them. From the quantum fields that give rise to particles to the enigmatic forces driving the expansion of the universe, each theory opens a door to a world of wonder and possibility. So buckle up and get ready to embark on a journey that will stretch your mind and leave you questioning everything you thought you knew about the cosmos. By the end of this video, you'll have a glimpse into the hidden layers of the universe and maybe even a new perspective on the mysteries that surround us. Let's begin. Now, let's step into the realm of the unseen, where the very fabric of reality is woven by forces we can't see but know are there. Our first theory takes us to the heart of modern physics, quantum field theory. At its core, this theory suggests that the universe isn't just filled with particles like electrons or quarks, it's brimming with invisible fields that stretch across all of space and time. These fields are like the stage on which the drama of the universe plays out. Every particle we know, from the tiniest neutrino to the most massive quark, is actually just a ripple or vibration in these fields. Think of it like this: if the universe were an ocean, particles would be the waves and the fields would be the water itself. Without the fields, there would be no particles, no forces, and no universe as we know it. Quantum field theory doesn't just explain how particles come into existence, it also describes how they interact. The electromagnetic force, for example, arises from vibrations in the electromagnetic field, while the strong nuclear force emerges from the Gluon field. This theory is the backbone of the standard model of particle physics, and it's one of the most successful frameworks we have for understanding the fundamental nature of reality. But here's the kicker: these fields aren't just passive backdrops. They're dynamic, constantly fluctuating, and filled with energy even in what we might call empty space. This means that the vacuum of space isn't truly empty, it's a seething, bubbling sea of potential where particles can pop in and out of existence. Quantum field theory challenges us to rethink what we mean by nothingness and opens the door to a universe that's far more alive and interconnected than we ever imagined. As we move forward, keep this idea in mind. The universe isn't just made of things, it's made of fields, and those fields are the hidden threads that tie everything together. Now, let's turn our attention to one of the most groundbreaking discoveries in modern physics, the Higgs Field. This invisible field is the reason particles have mass, and without it, the universe as we know it simply wouldn't exist. Imagine a room filled with people, and as you try to move through the crowd, you feel resistance. That's kind of how the Higgs field works. Particles interact with this field, and the strength of that interaction determines their mass. Some particles, like photons, glide through without a hitch, which is why they're massless. Others, like electrons and quarks, feel that resistance, giving them the mass we observe. The story of the Higgs field took a monumental leap forward in 2012 when scientists at the Large Hadron Collider announced the discovery of the Higgs boson, a particle that's like a ripple in the Higgs field. This discovery was a triumph for the standard model of particle physics, confirming a theory that had been proposed decades earlier. The Higgs field isn't just a theoretical idea. It's a fundamental part of the framework that explains how the universe works at its most basic level. But why is this field so important? Without the Higgs field, particles wouldn't have mass, and without mass, they wouldn't clump together to form atoms, stars, planets, or even us. It's the Higgs field that gives structure to the universe, allowing matter to exist in the way it does. This field is also a key player in the early moments of the cosmos, shaping how particles behaved just after the Big Bang. The discovery of the Higgs boson was a monumental achievement, but it also raised new questions. For instance, why is the Higgs field so weak compared to other fields? And what role does it play in the larger mysteries of the universe, like dark matter or the unification of forces? These are questions that physicists are still working to answer, and they remind us that even the most well-established theories can lead to new frontiers of exploration. As we continue our journey through the hidden fields of the universe, the Higgs field stands as a testament to the power of human curiosity and the relentless pursuit of knowledge. It's not just a cornerstone of modern science, it's a reminder that the universe is full of surprises, waiting to be uncovered. Next, we'll dive into another mysterious force that's shaping the cosmos in ways we're only beginning to understand: dark energy. Now, let's shift our focus to one of the most puzzling forces in the universe: dark energy. Unlike the Higgs field, which gives particles mass, dark energy is something entirely different. It's an invisible force that's causing the universe to expand at an ever-increasing rate. Think of it like this: if the universe were a balloon, dark energy would be the mysterious force blowing air into it, making it stretch faster and faster over time. The discovery of dark energy came as a shock to scientists in the late 1990s. Observations of distant supernova revealed that the universe wasn't just expanding, it was doing so at an accelerating pace. This was completely unexpected, as most physicists had assumed the expansion would slow down due to gravity. Instead, something was counteracting gravity's pull, pushing galaxies apart faster than ever before. That something is what we now call dark energy. But what exactly is dark energy? The truth is, we don't fully know. It's one of the biggest mysteries in modern physics. One leading idea is that dark energy is a property of space itself, a kind of energy inherent to the vacuum of empty space. This concept is tied to something called the cosmological constant, an idea first proposed by Albert Einstein. However, the amount of energy predicted by this theory doesn't match what we observe, leaving scientists with more questions than answers. Another possibility is that dark energy is a dynamic field, similar to the Higgs field but with very different effects. This field could change over time, influencing the rate of the universe's expansion in ways we don't yet understand. Some theories even suggest that dark energy might be connected to other hidden fields, like those we've already discussed, hinting at a deeper, unified framework that could explain all the forces of nature. The implications of dark energy are profound. If the universe continues to expand at this accelerated rate, it could lead to a future where galaxies are so far apart that they're no longer visible from one another. Stars would burn out and the cosmos would grow colder and darker, a scenario sometimes called the Big Freeze. On the other hand, if dark energy behaves differently than we think, it could lead to other outcomes like the Big Rip, where the expansion becomes so extreme that it tears apart galaxies, stars, and even atoms. Despite decades of research, dark energy remains one of the greatest unsolved puzzles in science. It challenges our understanding of gravity, space, and the very fabric of reality. As we continue to explore the hidden fields of the universe, dark energy stands as a reminder of how much we still have to learn. Next, we'll delve into another invisible force that shapes the cosmos: dark matter. Now, let's turn our attention to another invisible force shaping the cosmos: dark matter. Unlike dark energy, which drives the universe's expansion, dark matter is a mysterious substance that doesn't emit, absorb, or reflect light. It's completely invisible to our telescopes, yet its presence is felt through its gravitational effects. Imagine it as the unseen scaffolding of the universe, holding galaxies together and influencing their motion in ways we can't ignore. The story of dark matter begins with observations of galaxies. When astronomers measured how stars orbit the centers of galaxies, they found something strange. The outer stars were moving much faster than expected, as if there was more mass pulling on them than what we could see. This discrepancy led scientists to propose the existence of dark matter, an invisible field that interacts gravitationally but doesn't interact with light or other forms of electromagnetic radiation. In other words, it's there, but it doesn't shine, reflect, or block light in any way. So, what is dark matter made of? That's the million-dollar question. One leading idea is that it consists of particles that don't interact with ordinary matter except through gravity. These hypothetical particles, often called WIMP, short for weakly interacting massive particles, could be floating through space right now, passing through you and everything around you without a trace. Other theories suggest dark matter might be made up of axions, another type of hypothetical particle, or even primordial black holes formed in the early universe. But so far, despite decades of searching, we haven't directly detected dark matter particles, making it one of the most elusive mysteries in science. Dark matter plays a crucial role in the structure of the universe. Without it, galaxies as we know them wouldn't exist. Its gravitational pull acts like cosmic glue, holding galaxies together and allowing them to form in the first place. In fact, dark matter makes up about 27% of the universe's total mass and energy, while ordinary matter, the stuff we can see, accounts for less than 5%. That means the vast majority of the universe's matter is invisible to us, shaping the cosmos in ways we're only beginning to understand. The search for dark matter is ongoing, with scientists using a variety of methods to try and uncover its true nature. Underground detectors are designed to catch the rare interactions of dark matter particles with ordinary matter. Particle colliders, like the Large Hadron Collider, are smashing particles together in hopes of creating dark matter in the lab. And telescopes are scanning the skies for indirect evidence, such as the way dark matter bends light from distant galaxies, a phenomenon known as gravitational lensing. Despite all these efforts, dark matter remains a mystery. Its existence is undeniable given the gravitational effects we observe, but its true nature continues to elude us. As we explore the hidden fields of the universe, dark matter stands as a reminder of how much we still have to discover. Next, we'll dive into another fascinating concept, the Inflaton field, a hypothetical field thought to have driven the rapid expansion of the early universe. Now, let's shift our focus to a concept that takes us back to the very beginning of the universe, the Inflaton field. This hypothetical field is thought to have played a pivotal role in one of the most dramatic events in cosmic history, cosmic inflation. Imagine the universe just a fraction of a second after the Big Bang, expanding faster than the speed of light. This rapid expansion, driven by the Inflaton field, is what scientists believe set the stage for the universe we see today. The idea of cosmic inflation was proposed to solve some of the biggest puzzles in cosmology. For instance, why does the universe appear so uniform on large scales? No matter where we look, the distribution of galaxies and cosmic microwave background radiation is remarkably even. Without inflation, this uniformity would be hard to explain. The Inflaton field is thought to have smoothed out the early universe, stretching it so rapidly that any irregularities were ironed out, leaving behind the even, flat cosmos we observe. But the Inflaton field didn't just create uniformity, it also planted the seeds for the large-scale structure of the universe. Tiny quantum fluctuations in the Inflaton field were stretched to enormous scales during inflation. These fluctuations eventually became the building blocks for galaxies, galaxy clusters, and the cosmic web we see today. In a way, the Inflaton field is like the cosmic architect, laying the foundation for everything that followed. So, what exactly is the Inflaton field? It's a hypothetical scalar field, meaning it has a value at every point in space but no direction. Think of it as an invisible energy field that permeated the early universe, driving its exponential expansion. As the universe expanded, the energy of the Inflaton field gradually decreased, eventually causing inflation to end. This transition released a tremendous amount of energy, reheating the universe and giving rise to the particles and radiation that would later form stars, planets, and galaxies. While the Inflaton field is still a theoretical concept, it has become a cornerstone of modern cosmology. It elegantly explains not only the uniformity of the universe but also the origin of its structure. However, like many ideas in physics, it raises new questions. What caused the Inflaton field to exist in the first place, and what triggered its decay, ending inflation and giving birth to the universe as we know it? These are mysteries that scientists are still working to unravel. As we continue to explore the hidden fields of the universe, the Inflaton field stands as a testament to the power of theoretical physics. It shows us how even the most abstract ideas can provide profound insights into the nature of reality. Next, we'll turn our attention to another intriguing field, the Axion field, a hypothetical concept that could hold the key to understanding dark matter and the fundamental forces of nature. Now, let's venture into the realm of another fascinating hypothetical field, the Axion field. This mysterious concept introduces us to axions, particles that could hold the key to unlocking one of the universe's greatest mysteries, dark matter. But axions aren't just about dark matter. They also offer a potential solution to a puzzling issue in quantum chromodynamics, known as the strong CP problem. So, what exactly are axions and why are they so important? Axions are hypothetical particles that arise from a theoretical field proposed to address a specific challenge in particle physics. The strong CP problem revolves around the question of why certain interactions in the strong nuclear force, which binds quarks together, appear to be perfectly symmetrical. According to our current understanding, there's no obvious reason why this symmetry should exist, yet it does. Axions were introduced as a way to explain this symmetry naturally, without requiring fine-tuning of the universe's fundamental constants. But the Axion field doesn't stop there. It also has a strong connection to dark matter, the invisible substance that makes up a significant portion of the universe's mass. Unlike other dark matter candidates, such as WIMP weakly interacting massive particles, axions are incredibly light and interact very weakly with ordinary matter. This makes them extremely difficult to detect, but it also makes them a compelling candidate for dark matter. If axions exist, they could be everywhere, permeating the universe and contributing to its gravitational effects without ever being directly observed. The search for axions is one of the most exciting frontiers in modern physics. Experiments around the world are designed to detect these elusive particles, often using powerful magnetic fields and sensitive detectors. While no direct evidence of axions has been found yet, their discovery would be a monumental breakthrough, shedding light on both dark matter and the fundamental forces of nature. The Axion field represents a beautiful intersection of theoretical physics and observational science. It shows how solving one mystery, like the strong CP problem, can lead us to uncover deeper truths about the universe. As we continue to explore the hidden fields of the cosmos, the Axion field reminds us that even the smallest, most elusive particles can have a profound impact on our understanding of reality. Next, we'll turn our attention to a field that's far more familiar but no less intriguing, the gravitational field, as described by Einstein's theory of general relativity. Now, shifting our focus to a field that's both familiar and fundamental, let's explore the gravitational field. This invisible force, described by Einstein's theory of general relativity, is one of the most profound concepts in physics, shaping not just the motion of planets and stars but the very fabric of the universe itself. Einstein's groundbreaking idea was that gravity isn't just a force pulling objects together, as Newton described it. Instead, it's the result of massive objects warping the fabric of space-time. Imagine space-time as a giant, stretchy sheet. When you place a heavy object like a star or a planet on that sheet, it creates a dent. Other objects like moons or comets then move along the curves of that dent, following the path dictated by the warped spacetime. This is the essence of the gravitational field, a curvature in spacetime that guides the motion of everything within it. One of the most fascinating aspects of the gravitational field is its universal influence. From the tiniest particles to the largest galaxies, everything is affected by it. It's what keeps planets orbiting stars, stars orbiting the centers of galaxies, and even galaxies themselves bound together in clusters. Without the gravitational field, the universe as we know it would simply fall apart. But the gravitational field isn't just about holding things together. It also plays a key role in some of the most dramatic events in the cosmos. For example, when two massive objects like black holes or neutron stars collide, they create ripples in spacetime called gravitational waves. These waves, predicted by Einstein over a century ago and finally detected in 2015, are like echoes of the gravitational field itself, carrying information about the most violent and energetic events in the universe. The gravitational field also has a profound connection to time. According to general relativity, time runs slower in stronger gravitational fields. This means that a clock on Earth's surface ticks slightly slower than one in space, far from any massive object. This effect, known as gravitational time dilation, has been confirmed through experiments and even plays a role in the accuracy of GPS satellites. As we continue to study the gravitational field, we uncover more about the universe's structure and behavior. It's a field that not only shapes the cosmos but also connects us to the deepest mysteries of space and time. Next, we'll delve into another fundamental field that powers much of our modern world, the electromagnetic field, which governs light, electricity, and magnetism. Now, let's turn our attention to a field that's as essential to our daily lives as it is to the cosmos, the electromagnetic field. This invisible force is the backbone of light, electricity, and magnetism, and it's hard to overstate just how much it shapes both the natural world and the technology we rely on every day. At its core, the electromagnetic field is a dynamic interplay between electric and magnetic forces. These forces are carried by particles called photons, which are the fundamental units of light. When electric charges move or change, they create magnetic fields, and when magnetic fields change, they generate electric fields. This constant dance between the two is what we call electromagnetism, and it's the reason we have everything from the light in our homes to the signals that power our smartphones. One of the most remarkable things about the electromagnetic field is its role in light itself. Light is just a tiny slice of the electromagnetic spectrum, which includes everything from radio waves to gamma rays. Each type of electromagnetic wave has a different wavelength and energy, but they all travel through space at the same speed, the speed of light. This spectrum is what allows us to see the universe in so many ways, from the warmth of infrared radiation to the penetrating power of X-rays. But the electromagnetic field isn't just about light. It's also the force behind electricity and magnetism, two phenomena that have revolutionized human civilization. Think about it. Every time you flip a light switch, charge your phone, or use a computer, you're harnessing the power of the electromagnetic field. Even the Earth itself has a magnetic field, generated by the movement of molten iron in its core, which protects us from harmful solar radiation and guides compass needles. The electromagnetic field also plays a crucial role in our understanding of the universe. For example, it's through electromagnetic waves that astronomers observe distant stars, galaxies, and even the cosmic microwave background radiation, the faint afterglow of the Big Bang. Without the electromagnetic field, we'd be blind to much of the cosmos, and let's not forget its role in modern technology. From wireless communication to medical imaging, the electromagnetic field is at the heart of countless innovations. MRI machines, for instance, use powerful magnetic fields to create detailed images of the human body, while radio waves allow us to communicate across vast distances. As we explore the electromagnetic field, it's clear that this invisible force is not just a scientific concept, it's a fundamental part of our reality. It connects us to the universe, powers our world, and continues to inspire new discoveries. Next, we'll dive into another critical field that holds the very fabric of matter together, the strong nuclear force field. Now, shifting our focus to a force that operates on an entirely different scale, let's explore the strong nuclear force field. This is the glue that holds the very building blocks of matter together, binding quarks into protons and neutrons and ensuring atomic nuclei remain stable. Without this force, the universe as we know it simply wouldn't exist. The strong nuclear force is one of the four fundamental forces of nature, and it's by far the most powerful. It acts over incredibly short distances, only about the width of a single proton, but its strength is immense. To put it into perspective, if you could somehow magnify the strong force to the size of a human hand, it would be strong enough to lift a mountain. This force is what keeps quarks, the smallest known particles, tightly bound together to form protons and neutrons. But the strong nuclear force doesn't stop there. It also holds protons and neutrons together within the nucleus of an atom. You might wonder how this works, especially since protons, which are positively charged, naturally repel each other due to the electromagnetic force. This is where the strong nuclear force comes in. It overpowers the repulsion between protons, binding them together with neutrons to create stable atomic nuclei. Without this force, atoms would fly apart, and matter as we know it would disintegrate. The strong nuclear force is mediated by particles called gluons, which act like messengers carrying the force between quarks. Unlike photons, which mediate the electromagnetic force and can travel freely, gluons are confined within the particles they bind. This unique property is known as confinement, and it's one of the reasons why quarks are never found alone in nature. They're always bound together, either in pairs or triplets, forming protons, neutrons, and other particles. This force also plays a critical role in the energy that powers stars, including our Sun. Through a process called nuclear fusion, the strong nuclear force enables protons to overcome their repulsion and fuse together, releasing vast amounts of energy in the process. This is how stars shine and how heavier elements are formed, making the strong nuclear force not just a cornerstone of matter, but also a key player in the cosmic story. As we delve deeper into the mysteries of the universe, the strong nuclear force field reminds us of the delicate balance that holds everything together. From the tiniest quarks to the largest stars, this force is a testament to the intricate and interconnected nature of reality. Next, we'll turn our attention to another fundamental force that shapes the universe in its own unique way, the weak nuclear force field. Now, let's step into the realm of the weak nuclear force field, a fundamental force that operates on a scale even smaller than the strong nuclear force. While it may not be as powerful as its counterpart, the weak nuclear force plays a crucial role in shaping the universe, particularly in processes like radioactive decay and the interactions of elusive particles called neutrinos. The weak nuclear force is unique in its ability to change the very identity of particles. Unlike the strong force which binds particles together, the weak force is responsible for transforming one type of particle into another. This process is at the heart of radioactive decay, where unstable atomic nuclei release energy by transforming into more stable forms. For example, in a process called beta decay, a neutron can transform into a proton, emitting an electron and a neutrino in the process. This transformation is made possible by the weak nuclear force, which mediates the interaction through particles known as W and Z bosons. These W and Z bosons are the carriers of the weak force, much like gluons carry the strong force or photons carry the electromagnetic force. However, unlike photons, which are massless, W and Z bosons are incredibly heavy. This gives the weak force its short range, acting only over distances smaller than the size of an atomic nucleus. Despite its limited reach, the weak force has a profound impact on the universe. One of the most fascinating aspects of the weak nuclear force is its role in the early universe. In the first moments after the Big Bang, the weak force was instrumental in shaping the balance of matter and antimatter. It allowed for the creation of neutrinos, nearly massless particles that barely interact with matter but are essential to understanding the cosmos. Neutrinos, produced in vast quantities during nuclear reactions in stars and supernova, are a direct result of weak force interactions. In particle physics, the weak nuclear force is a cornerstone of the Standard Model, the framework that describes the fundamental particles and forces of nature. It's also deeply connected to the concept of symmetry breaking, which explains why the universe we see today is dominated by matter rather than antimatter. Without the weak force, the delicate processes that led to the formation of galaxies, stars, and ultimately life as we know it might never have occurred. As we continue to explore the mysteries of the universe, the weak nuclear force field reminds us of the subtle yet profound ways in which the smallest particles shape the largest structures. From radioactive decay to the birth of stars, this force is a testament to the intricate dance of particles that defines our reality. Next, we'll venture into a more speculative realm as we examine torsion fields and their potential role in the cosmos. Now, shifting our focus to a more speculative and intriguing concept, let's explore torsion fields. Unlike the well-established fields we've discussed so far, torsion fields exist on the fringes of physics, often associated with alternative theories and unconventional ideas. These fields are hypothesized to be a kind of twisting or rotational force within spacetime, potentially influencing everything from gravity to even consciousness itself. Torsion fields are thought to arise from the geometry of spacetime, where the fabric of the universe isn't just curved, as described by Einstein's general relativity, but also twisted. Proponents of this idea suggest that these fields could explain phenomena that mainstream physics struggles to account for, such as the modification of gravity or even the nature of human consciousness. Some theories propose that torsion fields might interact with biological systems, offering a bridge between the physical and the metaphysical. However, it's important to note that torsion fields remain highly controversial. While they've been explored in certain branches of theoretical physics, such as Einstein-Cartan theory, which extends general relativity to include torsion, they haven't gained widespread acceptance in the scientific community. Mainstream physics often views these ideas as speculative, lacking the experimental evidence needed to validate them. Despite their controversial status, torsion fields have captured the imagination of many researchers and thinkers. Some suggest that these fields could be harnessed for advanced technologies, such as anti-gravity devices or new forms of energy. Others see them as a potential key to understanding consciousness, proposing that the brain might generate or interact with torsion fields in ways we don't yet comprehend. While the scientific community remains skeptical, the exploration of torsion fields highlights the importance of pushing the boundaries of our understanding. Even if these ideas remain unproven, they remind us that the universe is full of mysteries waiting to be uncovered. As we continue our journey through the hidden fields of the cosmos, let's turn our attention to the zero-point field, a concept rooted in quantum mechanics that suggests even empty space is teeming with energy. Now, let's venture into the fascinating realm of the zero-point field, a concept that challenges our understanding of what it means for space to be empty. Unlike the torsion fields we just explored, the zero-point field is rooted in the well-established principles of quantum mechanics, yet it opens the door to some of the most mind-bending ideas in modern physics. The zero-point field refers to the energy that exists in the vacuum of space, even when it appears completely devoid of matter or radiation. According to quantum mechanics, empty space isn't truly empty. It's a seething, dynamic arena where particles and antiparticles constantly pop in and out of existence. This phenomenon, known as quantum fluctuations, gives rise to what's called zero-point energy, the lowest possible energy state of a quantum system. What makes the zero-point field so intriguing is its sheer scale. Even in the absence of any external forces, this field contains an astonishing amount of energy. In fact, if we could somehow tap into it, the zero-point energy in a single cubic meter of space could theoretically power entire cities. This has led to speculation about its potential applications in futuristic technologies, from limitless energy sources to advanced propulsion systems that could revolutionize space travel. But the implications of the zero-point field go far beyond technology. It also plays a crucial role in our understanding of quantum mechanics. For instance, the Casimir effect, where two uncharged metal plates placed close together in a vacuum experience an attractive force, is a direct consequence of the zero-point field. This effect has been experimentally verified, providing strong evidence for the existence of this mysterious energy. Despite its profound implications, harnessing zero-point energy remains a monumental challenge. The energy is spread out uniformly across space, making it difficult to extract or concentrate. Moreover, the theoretical frameworks needed to manipulate this energy are still in their infancy, leaving many questions unanswered. The zero-point field reminds us that even the emptiest parts of the universe are brimming with potential. It's a testament to the strange and wondrous nature of quantum mechanics, where nothing is ever truly still or silent. As we continue to explore the hidden fields of the cosmos, let's turn our attention to the scalar field, a concept that could hold the key to unifying some of the most fundamental forces in the universe. Now, shifting our focus to the scalar field, we enter a realm where simplicity meets profound complexity. Unlike vector fields, which have both magnitude and direction, scalar fields are defined solely by their magnitude. This seemingly straightforward characteristic makes them a cornerstone in some of the most groundbreaking theories in physics, including cosmic inflation and dark energy. Scalar fields are everywhere in the universe, though they often go unnoticed. Think of them as invisible, omnipresent entities that influence the fabric of reality without any directional bias. One of the most famous examples is the Higgs field, which we've already explored, but scalar fields extend far beyond just giving particles mass. They play a pivotal role in the early universe, particularly in the theory of cosmic inflation. According to this theory, a scalar field known as the Inflaton field drove the rapid expansion of the universe just moments after the Big Bang. This expansion smoothed out the cosmos, creating the uniform structure we observe today. Without scalar fields, the universe as we know it might never have formed. But the influence of scalar fields doesn't stop there. They are also central to our understanding of dark energy, the mysterious force accelerating the expansion of the universe. Some theories propose that dark energy could be the result of a scalar field permeating space, exerting a repulsive force that counteracts gravity on cosmic scales. What makes scalar fields so intriguing is their potential to unify the fundamental forces of nature. In the quest for a theory of everything, physicists have long sought a framework that combines gravity, electromagnetism, and the nuclear forces into a single, cohesive model. Scalar fields could be the missing link, offering a way to bridge the gap between quantum mechanics and general relativity. For instance, in string theory, scalar fields are associated with extra dimensions, providing a mathematical pathway to connect the forces that govern the universe. While this remains speculative, the possibilities are tantalizing. Could scalar fields hold the key to unlocking the deepest secrets of the cosmos? As we continue to explore the hidden fields of the universe, the scalar field stands out as a powerful tool for understanding both the past and the future of our cosmos. Its simplicity belies its potential to reshape our understanding of reality, offering a glimpse into the forces that shape everything from the smallest particles to the largest structures in the universe. Next, we'll delve into the vector field, a concept that adds direction to the mix, further enriching our understanding of the universe's hidden dynamics. Now, let's turn our attention to the vector field, where magnitude meets direction in a dynamic interplay that shapes some of the most fundamental forces in the universe. Unlike scalar fields, which are defined solely by their magnitude, vector fields add an extra layer of complexity by introducing direction into the equation. This combination makes them indispensable in modeling a wide range of physical phenomena, from the flow of water to the behavior of electromagnetic waves. Vector fields are everywhere around us, even if we don't always see them. Imagine the wind on a breezy day. Its speed and direction at any given point form a vector field. Similarly, the magnetic field around a bar magnet or the electric field surrounding a charged particle are classic examples of vector fields in action. These fields are not just abstract concepts, they are the backbone of our understanding of electromagnetism, one of the four fundamental forces of nature. In electromagnetism, vector fields describe how electric and magnetic forces propagate through space. For instance, the electric field around a charged particle points in the direction a positive test charge would move, while the magnetic field around a current-carrying wire forms concentric circles. These fields are governed by Maxwell's equations, a set of laws that unify electricity and magnetism into a single framework. Without vector fields, we wouldn't have the technology that powers our modern world, from electric motors to wireless communication. But the applications of vector fields extend far beyond electromagnetism. In fluid dynamics, they help us model the movement of liquids and gases, from the flow of blood through arteries to the circulation of air in the atmosphere. By assigning a vector to every point in a fluid, scientists can predict how it will behave under different conditions, whether it's the turbulence in a storm or the smooth flow of water through a pipe. What makes vector fields so powerful is their ability to capture both the strength and direction of a force or flow. This dual nature allows them to describe complex systems with remarkable precision. For example, in weather forecasting, vector fields are used to model wind patterns, enabling meteorologists to predict storms and other atmospheric events. Similarly, in engineering, they help design everything from aircraft wings to hydroelectric dams by simulating how forces interact with materials. Vector fields also play a crucial role in theoretical physics, particularly in the study of spacetime and gravity. In Einstein's theory of general relativity, the curvature of spacetime is described using tensor fields, which are a more advanced form of vector fields. These mathematical tools allow physicists to model the gravitational effects of massive objects like stars and black holes, providing insights into the structure and evolution of the universe. As we explore the hidden fields of the cosmos, the vector field stands out as a versatile and essential tool for understanding the forces that shape our reality. Its ability to combine magnitude and direction makes it a cornerstone of both theoretical and applied science, bridging the gap between abstract concepts and real-world applications. Next, we'll dive into the tensor field, a more complex but equally fascinating concept that takes our understanding of the universe's hidden dynamics to the next level. Now, let's take a step further into the realm of complexity with the tensor field, a concept that builds on the foundation of vector fields but takes our understanding of the universe's hidden dynamics to an entirely new level. Tensor fields are the mathematical tools that allow us to describe the curvature of spacetime, a cornerstone of Einstein's theory of general relativity. Unlike vector fields, which deal with magnitude and direction, tensor fields capture more intricate relationships, making them essential for modeling the gravitational forces that shape the cosmos. At its core, a tensor field is a way to represent how quantities vary across spacetime. Think of it as a more advanced version of a vector field, capable of handling multiple dimensions and directions simultaneously. In the context of general relativity, tensor fields describe how mass and energy warp the fabric of spacetime, creating what we perceive as gravity. This curvature isn't just a theoretical idea, it's the reason planets orbit stars, light bends around massive objects, and black holes trap everything, even light itself. One of the most famous examples of a tensor field is the Einstein field equations, which relate the curvature of spacetime to the distribution of matter and energy within it. These equations are the backbone of general relativity, providing a framework to understand everything from the motion of galaxies to the expansion of the universe. Without tensor fields, we wouldn't have the tools to explore phenomena like gravitational waves, ripples in spacetime caused by cataclysmic events such as colliding black holes. Tensor fields also play a crucial role in our understanding of black holes. These mysterious objects are regions of spacetime where gravity is so intense that nothing, not even light, can escape. By using tensor fields, physicists can model the extreme curvature of spacetime near a black hole's event horizon, the boundary beyond which escape is impossible. This helps us understand not only how black holes form and evolve, but also how they influence their surroundings, from bending light to distorting time itself. But the applications of tensor fields don't stop there. They are also key to understanding the large-scale structure of the universe. The cosmic microwave background, the afterglow of the Big Bang, contains subtle variations that tensor fields help us analyze. These variations reveal how matter and energy were distributed in the early universe, offering clues about the forces that drove cosmic inflation and shaped the universe we see today. What makes tensor fields so powerful is their ability to handle complex, multidimensional relationships with precision. Whether it's modeling the gravitational pull of a star, the warping of spacetime around a black hole, or the expansion of the universe itself, tensor fields provide the mathematical language to describe these phenomena. They bridge the gap between abstract theory and observable reality, helping us unlock the secrets of the cosmos. As we continue our journey through the hidden fields of the universe, the tensor field stands as a testament to the elegance and complexity of the laws that govern our reality. It's a reminder that even the most mysterious aspects of the cosmos can be understood through the language of mathematics and physics. Next, we'll explore the Chameleon field, a fascinating concept that suggests some hidden fields might adapt to their environment, offering new insights into the nature of dark energy and gravity. Now, shifting our focus to a field that seems almost alive in its adaptability, let's dive into the Chameleon field. This hypothetical scalar field is unlike any we've discussed so far, as it has the unique ability to change its properties based on its surroundings. Imagine a chameleon blending into its environment. This field operates in a similar way, adjusting itself depending on the density of matter around it. This fascinating behavior makes the Chameleon field a compelling candidate for explaining some of the universe's most puzzling mysteries, including dark energy and the nature of gravity itself. The Chameleon field is a scalar field, meaning it has magnitude but no direction. What sets it apart is its interaction with matter. In regions of high density, like near massive objects or within galaxies, the field becomes screened, effectively hiding its effects. This screening mechanism allows the field to avoid detection in local experiments, making it incredibly difficult to observe directly. However, in regions of low density, such as the vast voids between galaxies, the field becomes more active, potentially driving the accelerated expansion of the universe, a phenomenon we attribute to dark energy. One of the most intriguing aspects of the Chameleon field is its potential to modify our understanding of gravity. While Einstein's theory of general relativity has been incredibly successful in explaining gravitational phenomena, it struggles to account for the effects of dark energy. The Chameleon field offers a way to reconcile these discrepancies by introducing a new force that behaves differently depending on the environment. In dense regions, it aligns with general relativity, but in sparse regions, it could produce effects that mimic dark energy, providing a unified explanation for both gravity and cosmic acceleration. This adaptability also makes the Chameleon field a key player in theories of modified gravity. Some physicists propose that gravity itself might not be a constant force but could vary depending on the scale or environment. The Chameleon field fits neatly into this idea, offering a framework where gravity's strength and behavior could change in ways that align with observations of the universe's large-scale structure. Despite its theoretical appeal, the Chameleon field remains elusive. Experiments designed to detect its effects have so far come up empty, but this hasn't deterred scientists. The field's ability to hide in dense environments makes it a challenging target, but ongoing research continues to refine our methods for uncovering its secrets. If discovered, the Chameleon field could revolutionize our understanding of the universe, providing answers to questions about dark energy, gravity, and the ultimate fate of the cosmos. As we move forward, the Chameleon field reminds us that the universe is full of surprises. Its ability to adapt and hide challenges our assumptions and pushes the boundaries of what we think is possible. Next, we'll explore another intriguing concept, the Dilaton field, and its role in unifying the fundamental forces of nature. Now, let's turn our attention to a concept that bridges the gap between the known and the unknown, the Dilaton field. This theoretical field is a cornerstone of string theory, a framework that seeks to unify all the fundamental forces of nature, including gravity, into a single, elegant description of the universe. The Dilaton field plays a crucial role in this ambitious endeavor, acting as a kind of cosmic mediator that connects the forces we observe with the hidden dimension string theory proposes. At its core, the Dilaton field is a scalar field, much like the Chameleon field we just explored, but with a unique twist. It doesn't just influence matter or energy, it interacts with the very fabric of spacetime itself. In string theory, the Dilaton field determines the strength of the interactions between strings, the tiny, vibrating entities that are thought to be the fundamental building blocks of everything in the universe. By modulating these interactions, the Dilaton field effectively controls how the forces of nature behave, from the strong nuclear force that binds atomic nuclei to the gravitational force that shapes the cosmos. One of the most fascinating aspects of the Dilaton field is its connection to extra dimensions. String theory suggests that our universe may have more than the 3 spatial dimensions we experience. In fact, it proposes up to 10 or even 11 dimensions, most of which are curled up or hidden from our perception. The Dilaton field is intimately tied to these extra dimensions, influencing how they curve and compactify. This relationship is key to understanding how gravity, which operates in all dimensions, can appear so weak in our 3-dimensional world compared to the other forces. The Dilaton field also offers a potential solution to one of the biggest challenges in physics, unifying gravity with quantum mechanics. While general relativity describes gravity as the curvature of spacetime, quantum mechanics governs the behavior of particles at the smallest scales. These two frameworks have proven incredibly difficult to reconcile, but the Dilaton field provides a pathway. By acting as a bridge between the geometry of spacetime and the quantum behavior of strings, it could help us develop a theory of quantum gravity, bringing us closer to a complete understanding of the universe. Despite its theoretical promise, the Dilaton field remains a subject of intense research and debate. Detecting its effects directly is a monumental challenge, as it would require evidence of extra dimensions or the behavior of strings, phenomena that are far beyond our current experimental capabilities. However, the Dilaton field continues to inspire physicists, offering a tantalizing glimpse into a universe far more complex and interconnected than we ever imagined. As we continue our journey through the hidden fields of the universe, the Dilaton field reminds us of the profound connections that may exist between the forces we know and the mysteries we have yet to uncover. Next, we'll explore another dynamic field, Quintessence, and its potential to explain the enigmatic force driving the universe's accelerated expansion. Now, shifting our focus to another intriguing concept, let's dive into the Quintessence field, a dynamic and evolving field that has been proposed as a possible explanation for dark energy. Unlike the cosmological constant, which represents a static form of energy uniformly filling space, quintessence is a dynamic field that can change over time and space. This flexibility makes it a compelling candidate for explaining the accelerated expansion of the universe, one of the most profound mysteries in modern cosmology. The cosmological constant, introduced by Einstein, suggests that dark energy is a fixed property of space itself, unchanging and uniform. While this idea fits many observations, it leaves unanswered questions about why the value of this constant is so precisely tuned to allow for the universe we observe. Quintessence, on the other hand, offers a more nuanced explanation. As a dynamic field, it can vary in strength and density, potentially providing a natural explanation for the observed acceleration without requiring such fine-tuning. One of the key features of quintessence is its ability to evolve. In the early universe, it might have behaved differently, perhaps even contributing to the rapid expansion during cosmic inflation. Over time, as the universe expanded and cooled, the quintessence field could have transitioned into its current form, driving the accelerated expansion we see today. This adaptability makes it a versatile tool for cosmologists, offering a way to address multiple cosmic puzzles with a single framework. Another advantage of quintessence is its potential to unify different aspects of cosmology. For instance, it could provide a link between dark energy and other fundamental forces or fields, such as the Inflaton field responsible for cosmic inflation. By exploring these connections, scientists hope to uncover deeper insights into the nature of the universe and the forces that shape it. However, quintessence is not without its challenges. Detecting its presence directly is incredibly difficult, as its effects are subtle and spread across vast cosmic distances. Additionally, its properties must be carefully fine-tuned to match observational data, raising questions about whether it truly offers a simpler explanation than the cosmological constant. Despite these hurdles, the quintessence field remains a vibrant area of research, inspiring new ideas and experiments aimed at uncovering the true nature of dark energy. As we continue to probe the mysteries of the cosmos, the quintessence field reminds us that the universe is far from static. It is a dynamic, ever-changing tapestry of forces and fields, each playing a role in shaping the grand story of existence. Next, we'll explore another speculative concept, the phantom field, and its dramatic implications for the ultimate fate of the universe. Now, let's venture into the realm of the phantom field, a concept that pushes the boundaries of our understanding of the universe. Unlike the quintessence field we just explored, the phantom field is a speculative idea that introduces a startling twist: negative kinetic energy. This unusual property sets it apart from other fields and opens the door to some truly dramatic possibilities for the fate of the cosmos. At its core, the phantom field is a hypothetical field that could explain the accelerated expansion of the universe, much like dark energy. However, what makes it unique is its negative kinetic energy, which means it doesn't just accelerate expansion, it does so at an ever-increasing rate. Over time, this could lead to a scenario known as the Big Rip, where the universe's expansion becomes so extreme that it tears apart galaxies, stars, and even atoms themselves. The Big Rip is one of the most dramatic predictions in cosmology. Imagine a universe where the expansion force grows so strong that it overcomes all other forces: gravity, electromagnetism, even the strong nuclear force that holds atomic nuclei together. In this scenario, the universe wouldn't just expand, it would unravel completely, leaving behind a cold, empty void. While this might sound like science fiction, the phantom field offers a theoretical framework that makes such a fate possible. One of the key questions surrounding the phantom field is whether it could exist in the first place. Negative kinetic energy is a highly unusual concept, and it challenges many of the principles we take for granted in physics. For instance, it raises questions about energy conservation and the stability of the universe. If such a field exists, it would require a radical rethinking of our understanding of energy and matter. Despite its speculative nature, the phantom field has captured the imagination of cosmologists because it provides a way to explore the extremes of cosmic evolution. It also highlights how much we still have to learn about the forces shaping the universe. While the Big Rip remains a distant and uncertain possibility, the phantom field reminds us that the cosmos is full of surprises and our understanding of it is still evolving. As we continue to explore the mysteries of hidden fields, the phantom field stands as a testament to the creativity and curiosity driving modern physics. Next, we'll turn our attention to another fascinating concept, the Kalb-Ramond field, and its potential role in higher dimensional physics. Now, shifting our focus to another intriguing concept, let's explore the Kalb-Ramond field, a theoretical idea that emerges from the fascinating world of string theory. Unlike the fields we've discussed so far, the Kalb-Ramond field introduces a unique twist by describing antisymmetric tensor fields, a mathematical construct that plays a key role in higher dimensional physics. In string theory, the Kalb-Ramond field is thought to represent a kind of hidden force that interacts with strings, the fundamental building blocks of the universe in this framework. These antisymmetric tensor fields are different from the more familiar vector or scalar fields because they don't have a straightforward direction or magnitude. Instead, they describe more complex relationships between dimensions, offering a way to model interactions that go beyond our everyday experience of space and time. One of the most exciting aspects of the Kalb-Ramond field is its potential connection to higher dimensions. String theory suggests that our universe might have more than the 3 spatial dimensions we're used to, possibly up to 10 or even 11 dimensions. The Kalb-Ramond field could be a key player in explaining how these extra dimensions are structured and how they influence the behavior of particles and forces in our observable universe. For example, some theories propose that the Kalb-Ramond field might help explain phenomena like gravity's weakness compared to other fundamental forces. If gravity is leaking into higher dimensions, as some models suggest, the Kalb-Ramond field could provide a mechanism for how this happens. This idea opens up new possibilities for unifying gravity with the other forces, a major goal in modern physics. However, like many concepts in string theory, the Kalb-Ramond field remains speculative. While it offers a compelling framework for exploring higher dimensional physics, it has yet to be confirmed by experimental evidence. This doesn't diminish its importance, though. The Kalb-Ramond field represents a bold step toward understanding the deeper layers of reality, challenging us to think beyond the limits of our current knowledge. As we continue to unravel the mysteries of hidden fields, the Kalb-Ramond field reminds us that the universe might be far more complex and far more interconnected than we ever imagined. Next, we'll dive into the concept of tachyons and their hypothetical field, exploring how these faster-than-light particles could challenge our understanding of time and causality. Now, let's venture into the realm of the extraordinary with the Tachyon Field, a concept that pushes the boundaries of our understanding of physics. Tachyons are hypothetical particles that, if they exist, would travel faster than the speed of light. Unlike anything we've encountered in the observable universe, tachyons challenge the very foundations of causality and time as we know them. The idea of tachyons stems from the equations of special relativity, which allow for the possibility of particles with imaginary mass. While this might sound like science fiction, it's a legitimate mathematical prediction. These particles, if real, would be associated with a tachyon field, a field that could enable faster-than-light motion. But here's the catch: tachyons don't slow down to the speed of light like ordinary particles. Instead, they're always moving faster, making them impossible to observe directly under normal circumstances. One of the most intriguing aspects of tachyons is their potential to disrupt our understanding of cause and effect. In our everyday experience, cause always precedes effect. But if tachyons exist, they could theoretically allow information or influence to travel backward in time, creating scenarios where effect precedes cause. This raises profound questions about the nature of time and whether the universe's laws are as rigid as we think. Some theories suggest that tachyons could be linked to phenomena like wormholes or time loops, offering a mechanism for time travel. While this remains speculative, it's a fascinating area of exploration that bridges the gap between theoretical physics and the imaginative possibilities of science fiction. However, it's important to note that tachyons remain purely hypothetical. No experimental evidence has confirmed their existence, and their behavior would require a complete rethinking of our current physical laws. Despite this, the Tachyon Field serves as a reminder that the universe might hold surprises that defy our expectations. As we ponder the implications of tachyons, we're reminded that the cosmos is full of mysteries waiting to be uncovered. Next, we'll turn our attention to the Graviton Field, a hypothetical quantum field that could hold the key to unifying gravity with the other fundamental forces. Now, shifting our focus to another fascinating concept, let's explore the Graviton Field, a hypothetical quantum field that could revolutionize our understanding of gravity. Unlike the familiar gravitational force described by Einstein's general relativity, the Graviton Field represents gravity in the quantum realm, where particles and fields govern the fundamental forces of nature. At the heart of this idea is the graviton, a theoretical particle that would mediate the force of gravity, much like photons mediate electromagnetism. If gravitons exist, they would be massless, chargeless, and travel at the speed of light, acting as the building blocks of the gravitational field. This concept is central to the quest for a unified theory of physics, one that bridges the gap between quantum mechanics and general relativity, two frameworks that, despite their success, remain stubbornly incompatible. General relativity describes gravity as the curvature of spacetime caused by massive objects, while quantum mechanics deals with the behavior of particles and forces at the smallest scales. The Graviton Field offers a potential bridge between these two worlds, suggesting that gravity, like the other fundamental forces, could be quantized. This would mean that gravity operates through discrete packets of energy gravitons rather than as a continuous field. However, detecting gravitons is an enormous challenge. Gravity is incredibly weak compared to other forces, making it nearly impossible to observe its quantum effects directly. Despite this, physicists continue to search for indirect evidence such as gravitational waves, which were first detected in 2015. These ripples in spacetime, predicted by Einstein, provide a glimpse into the nature of gravity, but have yet to reveal the existence of gravitons. The Graviton Field also plays a crucial role in string theory, a leading candidate for a unified theory of physics. In string theory, gravitons emerge as vibrational modes of tiny, one-dimensional strings, offering a potential pathway to reconcile quantum mechanics and general relativity. While this remains speculative, it highlights the Graviton Field's significance in the ongoing search for a deeper understanding of the universe. As we consider the implications of the Graviton Field, we're reminded of the profound mysteries that still surround gravity. Could this elusive field hold the key to unifying the forces of nature? Next, we'll delve into the Neutrino Field, a subtle yet essential component of the universe's hidden fabric. Now, let's turn our attention to the Neutrino Field, a subtle yet profoundly important aspect of the universe's hidden framework. This field gives rise to neutrinos, some of the most elusive particles in existence. Neutrinos are nearly massless, electrically neutral, and interact so weakly with matter that they can pass through entire planets without a single collision. Despite their ghostly nature, these particles play a critical role in both astrophysics and particle physics, offering us a unique window into the workings of the cosmos. Neutrinos are produced in vast quantities by nuclear reactions, such as those occurring in the cores of stars during supernova explosions and even in nuclear reactors here on Earth. In fact, the Sun alone sends trillions of neutrinos streaming through your body every second, completely unnoticed. Their ability to travel through matter almost unimpeded makes them incredibly challenging to detect, yet their presence is a testament to the dynamic processes shaping the universe. In astrophysics, neutrinos serve as cosmic messengers, carrying information from the most extreme environments in the universe. For instance, when a massive star collapses in a supernova, neutrinos are among the first signals to escape, providing crucial insights into the mechanisms of stellar death. The detection of neutrinos from supernova 1987 marked a milestone in astronomy, confirming theoretical predictions and opening a new avenue for observing the universe. In particle physics, neutrinos are equally fascinating. They come in three types or flavors: electron neutrinos, muon neutrinos, and tau neutrinos, and have the peculiar ability to oscillate or change from one flavor to another as they travel. This phenomenon, known as neutrino oscillation, implies that neutrinos have mass, albeit incredibly small, challenging the original assumption that they were completely massless. This discovery has profound implications for the standard model of particle physics, hinting at new physics beyond our current understanding. The neutrino field, though invisible and intangible, is a cornerstone of our exploration into the universe's deepest mysteries. By studying neutrinos, scientists hope to unravel questions about the nature of dark matter, the asymmetry between matter and antimatter, and the fundamental properties of particles. These ghostly particles, born from the neutrino field, remind us that even the most elusive elements of the universe hold the keys to understanding its grand design. As we continue our journey through the hidden fields of the cosmos, our next stop will take us to the intriguing concept of the magnetic monopole field, a theoretical idea that could reshape our understanding of magnetism and the forces that govern the universe. Now, shifting our focus to another fascinating concept, let's explore the magnetic monopole field, a theoretical idea that could revolutionize our understanding of magnetism. Unlike the familiar magnets we encounter in everyday life, which always have both a north and a south pole, magnetic monopoles are hypothetical particles that carry just a single magnetic charge, either north or south. This idea challenges one of the fundamental principles of classical electromagnetism, which states that magnetic poles always come in pairs. The concept of magnetic monopoles isn't new. It was first proposed by physicist Paul Dirac in the 1930s as a way to explain why electric charge is quantized, why it comes in discrete, indivisible units. Dirac showed that if magnetic monopoles exist, they would provide a natural explanation for this phenomenon. This idea has since become a cornerstone of many grand unified theories, which aim to combine the electromagnetic, weak, and strong nuclear forces into a single framework. In these theories, magnetic monopoles are predicted to have formed in the early universe during a phase transition when the fundamental forces began to separate from one another. If they exist, they would be incredibly massive and rare, making them extremely difficult to detect. Despite decades of searching, no definitive evidence of magnetic monopoles has been found, but their discovery would be a monumental breakthrough in physics. The implications of magnetic monopoles extend far beyond their role in grand unified theories. They could also provide insights into the nature of space-time and the structure of the universe. For instance, some theories suggest that monopoles could be connected by cosmic strings, one-dimensional defects in space-time, creating a network that influences the large-scale structure of the cosmos. Additionally, their existence could shed light on the asymmetry between matter and antimatter, one of the greatest unsolved mysteries in physics. While magnetic monopoles remain elusive, their theoretical significance keeps them at the forefront of scientific exploration. Their discovery would not only validate key predictions of grand unified theories, but also open up new avenues for understanding the fundamental forces that shape our universe. As we continue to probe the hidden fields of the cosmos, the search for magnetic monopoles reminds us that even the most speculative ideas can lead to profound insights. Next, we'll delve into the cosmic string field, another intriguing concept that ties into the fabric of space-time and the early universe. Now, let's turn our attention to another captivating idea that stretches the boundaries of our understanding, the cosmic string field. Imagine the fabric of space-time not as a smooth, unbroken surface, but as a tapestry woven with tiny, thread-like imperfections. These imperfections, known as cosmic strings, are hypothetical one-dimensional defects that could have formed in the early universe moments after the Big Bang. Unlike the cosmic strings you might picture in science fiction, these are not physical ropes but rather incredibly thin, incredibly dense regions of energy that stretch across the cosmos. Cosmic strings are thought to have emerged during a phase transition in the early universe, much like cracks forming in ice as water freezes. As the universe expanded and cooled, the fundamental forces and fields underwent dramatic changes, and these transitions could have left behind these one-dimensional scars in spacetime. If they exist, cosmic strings would be astonishingly thin, no wider than a proton, yet unimaginably dense, with masses comparable to entire galaxies packed into a single strand. The role of cosmic strings in the early universe is a topic of intense speculation. Some theories suggest they could have acted as cosmic seeds, influencing the distribution of matter and energy that eventually led to the formation of galaxies and large-scale structures we see today. Others propose that cosmic strings might be connected to other hidden fields, such as the magnetic monopole field we just discussed, creating a complex web of interactions that shaped the universe's evolution. One of the most intriguing aspects of cosmic strings is their potential to produce gravitational waves, ripples in spacetime caused by violent cosmic events. If cosmic strings exist, they could vibrate or snap, sending out bursts of gravitational waves that we might detect with advanced observatories. This would not only confirm their existence, but also provide a new window into the universe's earliest moments. While cosmic strings remain theoretical, their study offers a fascinating glimpse into the hidden fields and forces that govern our universe. They remind us that even the smallest imperfections in spacetime could hold the key to understanding the cosmos on the grandest scales. As we continue to explore these ideas, we uncover new layers of complexity and beauty in the universe's hidden architecture. Next, we'll explore the domain wall field, another speculative concept that could reveal even more about the universe's mysterious structure. Now, shifting our focus to another fascinating concept, let's explore the domain wall field. Picture the universe not just as a vast expanse of space and time, but as a dynamic landscape filled with hidden structures. Among these structures are domain walls, hypothetical two-dimensional defects in spacetime that could have formed during the early moments of the universe. Unlike cosmic strings, which are one-dimensional, domain walls are flat, sheet-like regions where the properties of spacetime or fundamental fields change abruptly. These walls are thought to arise from phase transitions in the early universe, similar to how cosmic strings form. As the universe cooled and expanded, different regions of space might have settled into distinct states, creating boundaries between them. These boundaries, or domain walls, would act like cosmic membranes, separating areas with different physical properties. For example, imagine a bubble of space where the laws of physics are slightly different from the surrounding region. Domain walls would mark the edges of these bubbles. The existence of domain walls could have profound implications for the universe's structure. Some theories suggest that these walls might have influenced the distribution of matter and energy, shaping the large-scale patterns we observe today. They could also interact with other hidden fields, such as dark energy or dark matter, potentially playing a role in the universe's accelerated expansion or the formation of galaxies. One of the most intriguing possibilities is that domain walls could act as cosmic lenses, bending light and distorting the images of distant objects. This effect, known as gravitational lensing, could provide a way to detect these elusive structures. If domain walls exist, they might leave subtle imprints on the cosmic microwave background, the faint afterglow of the Big Bang offering clues about their presence and properties. However, domain walls also pose a challenge to our understanding of the universe. If they were too abundant or massive, they could disrupt the uniformity of the cosmos, creating observable anomalies that we haven't yet detected. This has led scientists to refine their theories, suggesting that domain walls might be rare, unstable, or confined to specific regions of the universe. While domain walls remain speculative, their study opens up exciting possibilities for uncovering the universe's hidden architecture. They remind us that even the most subtle features of space-time could hold the key to understanding the cosmos on the grandest scales. As we continue to explore these ideas, we uncover new layers of complexity and beauty in the universe's mysterious structure. Next, we'll delve into the Baryon Field, a fundamental concept that helps explain the very building blocks of matter in the universe. Now, let's turn our attention to the Baryon Field, a cornerstone of the universe's material makeup. This field is responsible for giving rise to protons and neutrons, the fundamental particles that form the nuclei of atoms. Without the Baryon Field, the very building blocks of matter as we know it wouldn't exist. It's through this field that the universe's tangible structure begins to take shape, from the smallest atoms to the largest galaxies. The Baryon Field plays a critical role in the formation of matter. Protons and neutrons, collectively known as baryons, are the heavyweights of the particle world. They make up the core of every atom, binding together to form atomic nuclei. This process, governed by the strong nuclear force, is what allows matter to clump together and create the complex structures we see around us. From the stars in the night sky to the cells in our bodies, the Baryon Field is at the heart of it all. But the Baryon Field's influence extends far beyond just creating matter. It also shapes the universe's overall composition. During the early moments of the cosmos, the Baryon Field determined how much ordinary matter, like protons and neutrons, would exist compared to other forms of energy and particles. This balance is crucial because it affects everything from the formation of galaxies to the distribution of elements in the universe. Without the precise tuning of the Baryon Field, the cosmos as we know it might look entirely different. One of the most fascinating aspects of the Baryon Field is its connection to the universe's asymmetry. In the early universe, there was a slight imbalance between matter and antimatter. For every billion particles of antimatter, there were 1,000,000,001 particles of matter. This tiny excess, preserved by the Baryon Field, is what allowed matter to dominate and form the stars, planets, and ultimately life itself. It's a delicate dance that highlights the field's profound role in shaping existence. Scientists continue to study the Baryon Field to better understand its properties and interactions. By examining how baryons behave in extreme environments, such as inside neutron stars or during high-energy particle collisions, researchers hope to uncover deeper insights into the nature of matter and the forces that govern it. These investigations not only shed light on the Baryon Field, but also help us piece together the larger puzzle of the universe's origins and evolution. As we explore the Baryon Field, we're reminded of how deeply interconnected the universe's hidden fields are. From the smallest particles to the grandest cosmic structures, these fields weave together the fabric of reality. Next, we'll dive into the Lepton field, which gives rise to particles like electrons and neutrinos, further expanding our understanding of the universe's intricate design. Now, shifting our focus to another fundamental piece of the cosmic puzzle, we arrive at the Lepton field. This field is responsible for generating particles like electrons and neutrinos, which play a vital role in the universe's structure and behavior. While the Baryon field gives us protons and neutrons, the Lepton field completes the picture by providing the lighter, more elusive particles that are equally essential to the fabric of reality. Electrons, one of the most well-known leptons, are the glue that holds atoms together. They orbit atomic nuclei, creating the electrical balance necessary for chemical reactions and the formation of molecules. Without electrons, atoms wouldn't be able to bond, and the complex chemistry that makes life possible simply wouldn't exist. But electrons are just one part of the lepton family. Neutrinos, on the other hand, are far more mysterious. These nearly massless particles rarely interact with matter, passing through entire planets as if they weren't even there. Yet, despite their ghostly nature, neutrinos are incredibly abundant, produced in vast quantities by stars, supernova, and even nuclear reactions here on Earth. The Lepton field is a cornerstone of the standard model of particle physics, which describes the fundamental forces and particles that make up the universe. In this framework, leptons are grouped into three generations, each consisting of an electron-like particle, a neutrino, and their heavier counterparts. This structure helps explain the diversity of particles and their interactions, offering a roadmap for understanding the universe at its most basic level. One of the most intriguing aspects of the Lepton field is its role in particle interactions. For example, during beta decay, a neutron transforms into a proton, emitting an electron and an electron-antineutrino in the process. This interaction is mediated by the weak nuclear force, one of the four fundamental forces, and highlights how leptons are deeply intertwined with the behavior of matter. Additionally, neutrinos, despite their weak interactions, have been found to oscillate between different types, a phenomenon that suggests they have mass, a discovery that has profound implications for physics and cosmology. The Lepton field also plays a crucial role in the early universe. During the first moments after the Big Bang, leptons and their antimatter counterparts were produced in abundance. As the universe cooled, most of these particles annihilated each other, leaving behind a small excess of matter, a process that echoes the asymmetry seen in the Baryon field. This delicate balance between leptons and baryons is what allowed the universe to evolve into the rich, complex structure we observe today. Scientists continue to study the Lepton field to uncover its secrets. Experiments like those conducted at particle colliders and neutrino observatories aim to measure the properties of leptons with incredible precision, shedding light on their behavior and interactions. These investigations not only deepen our understanding of the standard model, but also help us explore questions about the universe's origins, the nature of dark matter, and the possibility of new physics beyond our current theories. As we explore the Lepton field, we're reminded of how every particle, no matter how small or elusive, contributes to the grand tapestry of the cosmos. From the electrons that power our technology to the neutrinos that stream through space, the Lepton field is a testament to the universe's intricate design. Next, we'll delve into the Gluon field, which mediates the strong nuclear force and binds quarks together, further unraveling the mysteries of the universe's hidden fields. Now, turning our attention to the glue that holds the very fabric of matter together, we arrive at the Gluon field. This field is the force carrier for the strong nuclear force, one of the four fundamental forces of nature. Without the Gluon field, the universe as we know it would simply fall apart. It's the reason protons and neutrons exist, and it's what keeps atomic nuclei stable, allowing matter to form and persist. The Gluon field is unique because it doesn't just mediate the strong force, it actively participates in it. Gluons, the particles associated with this field, are responsible for binding quarks together to form protons, neutrons, and other particles known as hadrons. Unlike photons, which carry the electromagnetic force but don't interact with each other, gluons interact with one another, creating a complex web of forces that grows stronger as quarks move apart. This phenomenon, known as confinement, ensures that quarks are never found in isolation. They're always bound together, either in pairs or triplets, forming the building blocks of matter. Quantum chromodynamics, or QCD, is the theory that describes the behavior of the strong force and the gluon field. In this framework, quarks carry a property called color charge, which comes in three types: red, green, and blue. Gluons, on the other hand, carry a combination of color and anticolor charges, allowing them to interact with quarks and other gluons. This interplay of color charges is what gives the strong force its strength and complexity. It's also why the gluon field is so fascinating. It's a dynamic, ever-changing network of interactions that defies simple explanation. One of the most remarkable aspects of the gluon field is its role in the early universe. During the first moments after the Big Bang, the universe was so hot and dense that quarks and gluons existed in a state known as the quark-gluon plasma. In this primordial soup, quarks and gluons moved freely, unbound by the strong force. As the universe expanded and cooled, the gluon field began to take effect, binding quarks together and forming the first protons and neutrons. This transition marked a critical step in the evolution of the cosmos, setting the stage for the formation of atoms, stars, and galaxies. Today, scientists study the gluon field using powerful particle colliders, such as the Large Hadron Collider. By recreating the extreme conditions of the early universe, researchers can observe the behavior of quarks and gluons, shedding light on the fundamental nature of matter. These experiments have revealed surprising properties of the gluon field, such as its ability to generate glue balls, hypothetical particles made entirely of gluons. While glue balls have yet to be definitively observed, their existence would provide further evidence of the gluon field's complexity and importance. The gluon field is not just a theoretical curiosity, it's a cornerstone of our understanding of the universe. Without it, the strong force wouldn't exist, and neither would the protons and neutrons that make up the atoms in your body. It's a reminder that even the most invisible forces play a vital role in shaping reality. As we continue to explore the mysteries of the gluon field, we uncover deeper insights into the nature of matter, the origins of the universe, and the forces that hold it all together. Next, we'll explore the concept of the unified field, a theoretical framework that seeks to combine all fundamental forces into a single, elegant description of reality. Now, as we reach the culmination of our journey through the universe's hidden fields, we arrive at the grandest idea of all, the unified field. This concept represents the ultimate goal of physics, to combine all the fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force into a single, elegant framework. Imagine a universe where all these forces are not separate entities but different manifestations of one underlying field. This unified field theory, often referred to as the theory of everything, has the potential to solve some of the greatest mysteries in physics, from the nature of black holes to the origins of the cosmos itself. The idea of a unified field isn't new. Albert Einstein spent the latter part of his life searching for such a theory, hoping to merge gravity and electromagnetism into a single description. While he didn't succeed, his work laid the groundwork for future generations of physicists to continue the quest. Today, theories like string theory and loop quantum gravity are among the leading candidates for achieving this unification. These frameworks propose that at the most fundamental level, the universe is governed by a single set of principles, with all forces and particles emerging from the vibrations or interactions of tiny, one-dimensional strings or loops of spacetime. One of the most compelling aspects of a unified field theory is its potential to bridge the gap between quantum mechanics and general relativity. These two pillars of modern physics describe the universe at vastly different scales. Quantum mechanics governs the behavior of particles at the smallest levels, while general relativity explains the large-scale structure of spacetime. Yet they remain stubbornly incompatible. A unified field theory could reconcile these differences, offering a single set of equations that work seamlessly across all scales, from the subatomic to the cosmic. The implications of such a theory are profound. It could provide answers to questions that have puzzled scientists for decades, such as what happens inside a black hole or what caused the Big Bang. It might even reveal new dimensions of reality hidden from our current understanding. For instance, string theory suggests the existence of extraspatial dimensions curled up so tightly that we can't perceive them. If these dimensions exist, they could be the key to unlocking the unified field and understanding the true nature of the universe. However, the path to discovering a unified field theory is fraught with challenges. The energies required to test these ideas are far beyond what our current technology can achieve. Even the Large Hadron Collider, the most powerful particle accelerator ever built, can only scratch the surface of these high-energy regimes. Additionally, the mathematics involved is incredibly complex, requiring new tools and insights to make progress. Despite these obstacles, the pursuit of a unified field theory remains one of the most exciting and ambitious endeavors in science. As we reflect on the 30 theories we've explored, it's clear that hidden fields are more than just abstract concepts. They are the invisible threads that weave the fabric of reality. From the quantum fields that give rise to particles to the cosmic fields that shape the universe's expansion, these forces are the foundation of everything we know. The unified field represents the ultimate frontier, a vision of a universe where all these threads come together in a single, harmonious tapestry. While we may not yet have the answers, the journey to uncover them continues to inspire and challenge us, reminding us that the universe is far more mysterious and interconnected than we ever imagined. And with that, we conclude our exploration of the universe's hidden fields. If you've enjoyed this journey through the cosmos, don't forget to like, subscribe, and hit the notification bell to stay updated on our latest videos. The universe is full of secrets waiting to be discovered, and we can't wait to explore them with you. Until next time, keep looking up and wondering what else is out there. As we bring this exploration to a close, let's take a moment to reflect on the incredible journey we've taken through the universe's hidden fields. From the quantum fields that give particles their mass to the cosmic fields driving the expansion of the universe, each theory we've explored has peeled back another layer of the cosmos, revealing just how intricate and interconnected reality truly is. These 30 theories aren't just abstract ideas, they're the building blocks of our understanding, challenging us to rethink what we know about space, time, and existence itself. Hidden fields are more than just scientific concepts, they're the invisible forces shaping everything around us. They explain why stars shine, why galaxies spin, and why the universe behaves the way it does. Yet for all we've uncovered, there's still so much we don't know. The mysteries of dark energy, the nature of dark matter, and the quest for a unified field remind us that the universe is far from fully understood. Each theory we've discussed is a piece of a much larger puzzle, one that scientists are still working tirelessly to solve. What's truly remarkable is how these theories push the boundaries of human knowledge. They force us to confront questions that stretch the limits of our imagination. Are there hidden dimensions we can't see? Could the universe be governed by a single, elegant framework? And what other secrets lie waiting to be discovered? These aren't just questions for physicists, they're questions for all of us, inviting us to ponder our place in the cosmos and the nature of reality itself. As we wrap up, I encourage you to keep exploring these ideas. Share your thoughts in the comments below. What theory fascinated you the most? What cosmic mystery keeps you up at night? The universe is full of wonders, and the more we learn, the more we realize how much there is still to discover. If you've enjoyed this journey through the hidden fields of the universe, don't forget to like, subscribe, and hit the notification bell so you never miss an update. Together, let's keep unraveling the secrets of the cosmos, one theory at a time. Until next time, keep looking up and wondering what else is out there.